students, today we will continue the module 5 where we have left in the binary search tree. So first we will see the disadvantage of binary search tree. With the disadvantage we will go to the lecture of AVL tree. How those disadvantage was overcome using an AVL tree. First and foremost, whenever we are constructing the binary search tree, there is a possibility that it will form as a right skewed or left skewed tree. It means that consider if you have a sorted array of elements, say 10, 20, 30, 40, 50, so on. So the first element 10 will be the root node. Next the element need to be inserted is 20. The 20 will be checked against the root node, that is 10. 20 is greater than 10, so it will be inserted the right node of the root node, that is 10, and the right child will be 20. Next, likewise, the 30 will be inserted. Where it will be inserted is the root node is 10. Checked with the 30. 30 is greater than the root node. Next to the right node is 20. 20 is lesser than the node that to be inserted. So 10, 20, and 30 will form a skewed tree. So this is undesirable, and such complexity once again is big O of n. So to overcome this particular issue, we will go for an AVL tree. So AVL tree, the objectives of the AVL tree are we will give an introduction about the AVL tree and the operations, how the tree will be balanced. Okay, those things we will see using the concept called as an rotations. Okay, so those things we will see in today's class. Okay, so when searching is optimal in binary search trees, if you have n elements, then the height of the tree must be n minus 1. Then the search will follow the complexity of log n. If the number of if the number of nodes is equal to the number of depth, then or height, then the binary search tree is not optimal for searching. Okay, so that's the issue. So we will construct an AVL tree in such a way that the search complexity for whatever the node that we have inserted will be big O of log n. So this is how the AVL tree works. Okay, the operations we will see it now. So if you see this particular tree in the right side, we'll have a root node. Okay, whatever the node that we want to search will be available in log n time complexity. For example, if you want to search the node f, okay, so consider it is a number. First you will be searching this particular node. If the number that you want to search is greater than, then you will go to the right subtree. Once again you will search that key with the value that is in the C. If it is lesser than that, you will go to the left side, or else it is going to the right side. So if you notice carefully that this AVL tree fills the node level by level. Okay, you see this, the level 1 will have a node A. Next, which level you need to fill is the level 2, B and C is filled. Only when this level is filled, you need to move to the next level, that is you can fill 4 nodes in the level 3. Once this 4 nodes are completed, then only you can go to the level 4. The level 4 you can accommodate in total 8 nodes. So likewise you need to go, so that it is called as an height balanced tree. When the height is balanced, the search complexity is big O of log n. It will never be going to big O of n like a linear search. Okay, so to how to balance this tree is the first and foremost concept we need to understand is the balance factor. This AVL tree means the expansion is Adelson, Welsky and Landis. These are the scientists who invented this particular AVL tree. So this tree is named after them only. So this is called as an AVL tree. The AVL tree must follow two properties. Okay, so the properties are, we will have the root node. All the node left to the root node is lesser than the root node, and right node will be the greater than the root node. That's the first one. The second one is the balance factor. The balance factor means the height of the left subtree minus height of the right subtree. So the height of the left subtree minus height of the right subtree is what we call as balance factor. This balance factor must always be in the range of -1 to +1. Either it can take three values, that is -1, 0 and +1. If the value exceed this limits, okay, then the tree is called as an unbalanced. You need to do certain operation to balance that particular tree. Okay, now if you see this, this slide illustrates how do we calculate the balance factor. First we will see this D, okay, the D node in the first one. So if you see this, all the leaf node will have the balance factor of 0. How it is means the leaf node will not have, for example, this leaf node will not have the left subtree, at the same time it does not have the right subtree also. So left subtree is 0 and right subtree is 0. 0 minus 0, the leaf nodes will always carry a balance factor of 0. So if you see here, we have given the D and C node as 0, the balance factor is 0. You come to the node B node, if you see the height of the left subtree is 1, but the height of the right subtree is 0. So left subtree minus right subtree, 1 minus 0, the height at the node B is 1. Okay, so and if we check for the A node, the height of the left subtree, what is the left subtree? The height is 1 and 2. 2 minus the right subtree is 1. 2 minus 1 is equal to 1. So if you consider this particular node, this particular tree, the height is certainly balanced. So you don't need to do any balancing. Okay, this is already balanced. As I said already that whenever you are having a binary search tree or height balanced tree, you need to fill the nodes level by level. If you see this node, this particular tree, okay, you see this, the first level 1 will accommodate only one node, so it is one node, it is here. In the next level you can accommodate two nodes, so more than two nodes you cannot accommodate, then only you can go to level 3. You see this 1 2, in this level you can accommodate 4. If all the 4 nodes are filled, then only you need to go to the next level. That's the key principle that balance factor impacts. Okay, so if you see this particular node, if you see this one, okay, this is, of course, it is obviously an unbalanced binary search tree. So you have A, B, C, D and E. Okay, you see this, we will check the leaf node are E and C. Both this leaf node will have the balance factor of 0, of course. Okay, next we will have a node D. Okay, the height of the left subtree is 1, right subtree is 0. 1 minus 0, it is balanced at this particular level, considering the node D, it is already balanced. Now we will go to the node B. Okay, the height of the left subtree is 2, height of the right subtree is what? Only 0. So 2 minus 0, it is 2. The balance factor is 2 at the node B. So at this particular point, the node is unbalanced. This particular subtree is unbalanced. To overcome this unbalancing issue, we need to do an operation called as a rotation. There are 4 kinds of rotation. Okay, so this is once again an illustration of a balance factor calculation. So as I said already that the height of the leaf node's balancing factor is always 0. So if you take this 8 node, the left subtree is 0 minus the right subtree is 1. 0 minus 1, the balance factor is minus 1. Likewise, you can able to calculate, but as I said already that the balance factor should lies in a value minus 1, 0 and 1. If you see this, the node 11, which is having the balance factor of 2, which is an unbalanced. So at this position, you need to apply certain techniques called as a rotation to balance it, so that this particular node will not get the balance factor as 2. Instead of it will get the balance factor in the range 1, 0 and minus 1. Okay, this is just an illustration of calculating the balance factor. Okay, now the techniques used to balance the tree is what we call as rotations. Okay, there are 4 kinds of rotation. Those are single left rotation, right rotation, left right rotation, right left rotation. There are 2 major kinds. It is called as a single rotation and double rotation. So left rotation is called as a single rotation, left and right rotation is called as single rotation. Left right rotation and right left rotation are called as a double rotation. You see this here, the first 2 are single rotation, the next 2 are double rotation. Okay, so we will see this with an example. You can go through this. Okay, whenever you have time, you can go through this. Okay, consider a tree is like this. Okay, if we calculate the balance factor, you see this is 0. As a leaf node, the balance factor here it is 0. Okay, Okay, if you go to the node B, the balance factor, how do you calculate the balance factor is, okay, height of the left subtree minus the height of the right subtree. So 0 minus 1, minus 1 it is, they have given it as in 1, say no issues in it, minus or plus it doesn't matter. So here it is 1, the height of the left subtree minus height of the right subtree is 1. If you go to the node A, the height of the left subtree is what? 0, and the height of the right subtree is 1 and 2. 0 minus 2 it is 2. Okay, 2 minus 2 it is 2, you can say it as it doesn't matter. So this, at this particular point of time, the height is imbalanced at this particular node. So to overcome it, what you need to do is you need to do a rotation, and particular to this situation, the rotation you need to apply is what we call as left rotation. If you apply the left rotation, then you see this, the node A will come to the left side, and you see this, the balanced tree, the A will go to the left side of the B node, and C node will be as usual, it will be in the right side. So if you calculate the balance factor of the final tree, then it is the balanced, all of that will get the balance factor as 0, okay, which is in the range of the balancing factor. So you can do this left rotation to overcome it. The vice versa, it's the right rotation. If you see carefully here, the balancing is, the problem of balancing occur in the node C, which is having the balance factor of 2. Okay, if you see this, you can able to rotate this node to its right. That's why it is called as a right rotation. Once you do the right rotation, the nodes are balanced. So the balance factor, if you calculate, okay, 0, 0 and 10. Okay, sorry, 0. So next is what we call double rotation. If you listen carefully, previously it is what a kind of a skewed tree, either it is a left skewed or right skewed tree. Here it is kind of a zigzag. Okay, so you see this, the left and right, it will have like this. So to overcome these particular issue, you need to do a kind of a double rotation. Okay, for example, what you need to do is, first you need to do a left rotation in accordance to the node A. So the node A will go down, and the B node will be the parent of the A node. So now once again, if you see this, this is unbalanced. In this situation, what you can do is, you can do one more right rotation. So here it is a combination of left rotation and also a right rotation, then it is called as a double rotation. So this is zigzag. You just identify the pattern. If node is in the zigzag pattern and the imbalancing is happening in the node, so then you need to do a double rotation. Either it can be a left right rotation or else a right left rotation. Okay, so if you see this, first in this first two diagrams, we have applied just a left rotation. We identify the imbalance and we have applying the left rotation. In the third, we have completed the left rotation. Once we complete the rotation, the tree looks like root is C, the child is B, and B's child is A. Now once again, if you calculate the balance factor of this tree, so this is imbalanced in the node C. Once again, what you need to do is, you need to do a right rotation. So if you do right rotation, this will be your final tree. So we have avoided the imbalancing and we given to a balanced one. So here, if you see this, this is the tree. Okay, here we will apply right left rotation. If a right left rotation means C, the node C will go down and B will come to the position, and if you see A, B, C will be the tree. Okay, so and then we can construct the left rotation. If you do a left rotation, this will be balanced once again. So since now we have seen with the alphabets, let us work with a simple numbers. Okay, like I said. Okay, we will do this insertion, all those operations. Okay, so for that I will go to a website. So AVL trees are always also called as a balanced binary search tree. So now listen carefully that I will insert a node from 10 to say 50 or 60. First you see this, I am inserting the node 10. Okay, So the node 10 is going to be the root node, which are the node that I am inserting. Since there is only one node, so this is going to be the root node. Next I am going to insert 20. See, the level 1 cannot accommodate any more nodes, so we can extend the next node, the new node, to the level 2. Okay, you see this. So I am going to insert this. 20 is checked against the root node. Okay, so here it is inserted at the right. So in this example, in this particular example, the leaf node starts with 0. Okay, usually what we have seen is the balance factor for the leaf node is 0. Here in this animation they took it as 1. Okay, so you can check the balance factor. The allowed balance factor is like 2, 1, 0, all those things. So 2, 1, 0, you will not get 0 most of the time. So next is what I am inserting, the 30. You see this here, it is greater than that. Once again 30 is greater than that. See, here we will have an imbalancing considering all these three nodes. So what we need to do is we need to do a left rotation. So whenever you are going to do a left rotation, this node 20 will become root and 10 and 30 will become its right and left. Okay, next I want to insert 40. If you listen carefully, the level 1 is completely filled with only one node. Level 2 can accommodate two nodes. The two nodes are accommodated, say 10 and 30. If I am going to insert any nodes, it is going to be in the level 3. Okay, so I am going to insert the node 40. Okay, you see this. Once again it is checking. So level it is in the level 3. It is acceptable actually. Okay, so next I'm going to insert a node 50. Okay, see this here. It will check with the 20, it is greater. It checks with 30, it is greater. Next it checks with the 40, it is greater. So you need to insert at this. You check the balancing factor at this position. So here it became imbalance. You see this, the height is 3. So you balance it. Okay, once again it is already balanced because it is not extending more than the level 3. Okay, till how many nodes you can how many nodes can accommodate in the level 3 is 2 more nodes. So once again I am inserting say node 60, check it, 20. Next is it is checking with the 40. Next is 50. It's going to be the right side of this node. Okay, you see this is the special case. Okay, you pull this node. Okay, pull this node. Okay, and this going to be a special case. You see this, the root node is pulled once again because here in this node the height is same. Okay, I'll do a skip back. Okay, this is the previous tree. If I insert 60, okay, you check it here, you check this and check this and it will come down. Okay, but if you see the balance factor, it is balanced at this position. It is also balanced in this position, but it is not balanced at the root level. Okay, so this is a special case. Then the root node will go down and it is like a left rotation once again. But the node that is attached to the 50, the left child of the 50th node is 30. This will be pushed to the right child of 20. This is the one special case you need to remember very carefully. So next I will be inserting say node 70. If I insert this, you see this 40 will be compared, next will be compared with 50, it will be compared with 60, then 70 will come here. Okay, so if you do this left rotation here, imbalance will happen at this position. You do an imbalance, it will have what? So now you see this is balanced tree. So I have implemented till 7. So now you see this level 0, level 1 is filled, level 2 is filled, level 3 is filled. If I insert any more node now, it will be inserted at the level 4. Okay, for example I am inserting 80. Okay, you see this 40 it is checked, 60 it is once again it is checking, 70 it is checking. Once again where will be inserted? Right child of the 70. So now the tree is not imbalanced. Even if you check the balancing factor, it will not be an imbalanced one. Okay, done. So you can calculate the balance factor like how I taught you. This is just for an animation. Okay, so this is all about the AVL tree. Now what we are going to do is we will try to delete a few nodes. Okay, so now you listen carefully. So I am going to, there are two things. Okay, so now I am going to delete the leaf node. Okay, if I am going to delete the leaf node, say the leaf node is 80, it will be just like that, it will be deleted, there will be no issue. So next type is that a node with a single child. If suppose I am going to delete the node 70, for example 70 I am deleting. So if I'm deleting 70, first you need to search for the node 70. It is going to this, so it will be deleted and the child node will check its position. Okay, so this is how we will delete. So I'm going to do a skip back. Okay, skip back with the same tree. So if I delete the node 70, this child node will take its position. Now one more thing is, what happen if I delete a parent with the two child? For example, here we'll have 20. Who will take this particular node? You see this, who is in order predecessor. Okay, predecessor means before that. Okay, or else you can have in order successor, it's up to you. So either in order predecessor or in order successor will take its position. Now I am deleting the node 20. So here it is checking, so node 20 is available here. So we are going to take in order predecessor. Predecessor means before the node. Okay, this is an in order predecessor. Once you delete a particular node, once again you need to check the balance factor. If the balance factor is not it's violated, if it is the balance factor is violated, then once again you need to do the rebalancing using this left rotation or else the right rotation. So I'll go to the previous one, skip back. So what if happens if I'm going to delete the node 40? So who is the in order predecessor? You see this, the node 30 will be the in order predecessor. Okay, so the node 30 will come at that position. You see this here. I'm going to delete the 40. Okay, if it is 40 means who is the in order predecessor? 30. 30 will come here. Now you check the height. Okay, the balancing factor. If it is balanced, then it is okay. So this is how this AVL tree works. Okay, so in the next lecture we will see the red